Welcome back to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep from the Electrical Engineering Department at IIT Hyderabad. So today we will begin our penultimate module, which is the 8th module, which is about the introduction to neuromorphic computing. And in addition, we will see hardware implementation of neurons and synapses. But before that, let's do a very quick recap of the 7th module, our previous module, where we studied about AI/ML computing, because neuromorphic computing follows very naturally from what we studied the last time around. So we saw AI/ML computing, especially deep neural networks, from a very hardware-centric point of view. We saw how the history of AI/ML had its roller coaster ride of its ups and downs. And there were lull periods between the initial theoretical development and the application boom that we only saw in the 21st century. And the reason for that is that we did not have enough computational firepower to translate these ideas into useful applications. We defined what the AI/ML task is, which is essentially multi-dimensional curve fitting. And then we looked at how an artificial neuron performing both a combination of linear and non-linear operations. Remember, the linear operation was your multiply and accumulate operation, whereas your non-linear operation was your thresholding function. And when you scale these artificial neurons into large-scale deep neural networks, deep means several layers, you can do a lot of interesting classification recognition tasks. We also noted that the multiply and accumulate operation is the most energy and latency intensive task in ANNs. Furthermore, in our deep dive of convolution operation and associated convolution neural networks, it became very, very clear that even seemingly simple tasks from the perspective of a human being, like doing CAPTCHA, simple image classification, when you try to do that with convolution neural networks, it ends up requiring billions of parameters and several trillions of multiply and accumulate operations, requiring a very high power consumption, which is becoming very unsustainable even from an environmental perspective. And that naturally brings us to the motivation for today's module. So in addition to brain-inspired software or algorithms that we have seen in our previous module, there is also a need for brain-inspired hardware. And that is exactly the area of neuromorphic computing. And in this module, we will first ask, primarily in today's class, what exactly is this neuromorphic computing? Then we will look at the computational architecture of the brain, which is fundamentally built from neurons and synapses. And then we will explore whether we can design these electrical analogs of these neurons and synapses, how memory and storage devices, especially eNVMs, can serve as hardware versions of biological neurons and synapses, and how, at least in principle, these could be integrated into hardware of full-scale artificial neural networks. So with this roadmap, let us move forward. Remember, this was where we concluded our previous class. We basically looked at the computational efficiency of modern-day CPUs and GPUs and compared it to the human brain. Essentially, what we saw was modern-day GPUs and CPUs do a fantastic job at giving a lot of computational power, which is measured in TOPS or tera operations per second. But if you define the metric of power consumption per unit operation, that is watts per TOPS, how much energy or power is required per operation cycle, you see that there is a big disparity over orders of magnitude between your latest GPUs and TPUs and your human brain. And basically in this module, we will do a deep dive of why that is the case. But we had given you some hints saying that while the trend of modern day computing is that you just keep reducing or shrinking the dimensions of your transistor, and therefore you can operate these circuits at much larger clock frequencies. And as the clock frequency increases, the power density basically shoots up exponentially. But if you look at human brain or biological computation, it is in the other end of the spectrum. In contrast, the human brain operates at a meager 5 to 12 watts, 20 watts, with extremely low power density, yet it supports remarkable intelligence. And this contrast makes it very clear that if we want sustainable, low power AI/ML based computing, we need hardware also that is brain inspired. That is the idea. And to understand this, what we will do today is get a feel of what is the overall structure and a need of neuromorphic computing. So, from the last slide, we already saw that modern day CPUs and GPUs are very powerful, but their power efficiency is very, very poor compared to the human brain. So this leads to the question, how do we bridge this particular gap? On one side, we have your biological brain, which is sitting over here in a very small area and is doing all these pattern recognition and classification tasks. In these kind of data-driven compute, the latency and the power consumption of biological brain is very, very less. Also, the training efficiency is very high. What do you mean by training efficiency? The meaning of training efficiency is how much data sets do you need to expose your computing system before it can start making accurate classifications. So as you know, we gave the example of baby's brain. The training efficiency of the brain is also very large. And that is what motivated us to look at AI/ML algorithms, which is nothing but an attempt to mimic the biological computing in algorithms and in software. But we suffer from large power consumption, and the scale of the problems that we can solve are rather very simplistic, even after such high power consumption. And that is why the second generation of trying to mimic biological computing comes in the form of brain-inspired hardware, which is neuromorphic computing, which comprises not only of devices, but also architecture and circuits level innovations to build hardware that can deliver AI performance at fraction of the power or cost. So therefore, it is better to have a quick recap before we can contrast this with the next generation of computing, which is neuromorphic computing. So as we have seen in the past, the essential feature of von Neumann computing is that the CPU and memory are physically separate. Memory and logic are spatially and functionally separate. So all these instruction and data must shuttle back and forth over this shared bus, which connects the logic element and the memory element. This is quite efficient for general purpose computing, but it suffers from the von Neumann bottleneck, especially in data-driven computing. With its limited bandwidth and sequential execution, and so much power being wasted in shuttling data back and forth rather than the actual compute process. Important also to realize that everything is synchronized by a central or global clock, and computation happens essentially in a deterministic or logical manner by a set of instruction codes, if then else statements, if you break down it further into assembly level code. Another important feature of von Neumann computing is it is generally or 99.99% of the time implemented using digital computing only. That means your computer only understands bunch of zeros and ones. Contrast this with deep learning. What is deep learning? They are still built on von Neumann systems, but they exhibit much higher parallelism compared to your traditional von Neumann CPUs. So GPUs allow massively parallel dense compute processing thousands of multiply and accumulate operations at once. How do you do that? Because instead of having one powerful central processing unit or one core, what you do is you break down the compute power into several less powerful cores which can do these multiply and accumulate operations parallelly. They are still synchronous in nature, and although these are not governed by explicit rules, as is the case in von Neumann computing, there is still a lot of sequential processing which is happening through a synchronous clock. However, the training or learning is done primarily offline with large data sets which are pre-labeled, and this large training cycle also consumes a lot of power, and learning is still dependent on these synchronous clock cycles. This results in a lot of tremendous performance, but as we discussed, at the cost of very large power consumption and of large set of hyperparameters. Now, we are coming to neuromorphic computing. So, while deep learning made AI very practical, it did not solve the energy efficiency problem. So, on the right, we are introducing the new form of computing today called neuromorphic computing. Here, the ideal system is your human brain. So, before we go into neuromorphic computing, I want to explain this term and what it connotates to. When I say neuromorphic, I do not mean that you are trying to build a full-scale artificial brain with all its complex biophysical mechanisms. Instead, it focuses on copying or mimicking only certain principles like spikes, local memory, and parallelism that make the computation of the brain massively energy efficient. So, instead of having offline training with large data sets in neuromorphic systems, you can do learning on the fly. This is called unsupervised learning, something that we will see very soon, where you are adapting dynamically through something called local rules. Now, local rules is something that I will briefly discuss right now, but of course, details will come soon after. So, what is the meaning of local rules? Local rules means based on the previous firing of neurons, the weight of the synapses are automatically adjusted. Remember, in deep neural networks, the adjusting of the weights was also done computationally through this energy expensive backpropagation algorithm. In local rules, the synapses are set automatically, and we will see how that happens. We will look at learning rules like spike timing dependent plasticity in detail. Also, the most important thing is instead of a global synchronous clock, neuromorphic systems are essentially asynchronous event-driven computation, where all the neuronal firing happens only when an event occurs. And because there is no global clock running throughout the system, it drastically reduces the wasted energy. And instead of having dense all-to-all connectivity, neuromorphic hardware embraces sparseness. What is sparseness? Limited connectivity and parallel computation, where only a subset of neurons and synapses at a given time are active. But to conclude, we can say that what makes neuromorphic systems fundamentally different is that computation and memory, logic and memory are co-located. That means, unlike von Neumann computing, where there is a clear spatial and functional distinction between logic and memory, those lines have got completely blurred in the form of neurons and synapses which mimic the human brain. And this is what avoids the von Neumann bottleneck, and the power efficiency, at least in promise, is several orders of magnitude better, because computation and memory storage both is happening parallelly and locally. Because the concept of asynchronous event-driven computing is rather new, let us try to understand this with a few useful examples. So, what is your traditional computing which is synchronous, which involves a global clock? In this kind of computing, any incoming event is periodically polled. A simple example is that you are keeping on refreshing your email inbox every second to check whether a new email has arrived or not. This is more like a CPU or GPU that is always active because you're continuously polling and you're always checking even when nothing useful is happening. However, event-driven computing is essentially asynchronous. There is no global clock. This is similar to notification that comes on your phone, which is active only when a new email arrives. So you do not waste your time and energy constantly refreshing. And that is how even the brain or event-based sensors do computation. Things happen or energy is spent only when an external event is triggered. A simple way to understand that is also to see how human beings do driving. When you are driving through a street, you are not continuously looking for the red light signal. Like you're not continuously polling for the red signal to make a decision. But the moment there is a red signal that you see, immediately your foot goes on the brake. So while a computer will continuously check for the red signal, human brain is completely event driven. Another important way to look at this is through the idea of a vision camera versus an event-based camera. So let me run this simulation for you by looking at a normal vision camera versus a neuromorphic event-driven camera. When you are trying to image an example of this rotating disc, you see this rotating disc with a dot on it. While a normal camera will capture a series of frames continuously at a fixed rate, even when very little change is happening in the scene. That will lead to a lot of redundant data which is collected and a lot of energy that will be spent in processing the frames, which is containing mostly static information. And because you are loading the system so much, you will have larger latency. And if the disk starts spinning with a much higher frequency than the frames that you are able to capture, you will start losing information in form of these blurs that you see in camera. Let's contrast this with the bottom panel of an event-driven camera. So instead of recording the entire set of frames, the event-driven camera only detects changes in brightness. So if nothing is moving, nothing is recorded. But when there is motion, these pixels that change immediately generate spikes. And this gives you much higher temporal resolution, much higher bandwidth, and far lower latency. And this also leads to much reduced power consumption. So this is what illustrates the principle of event-driven computing, where computation is triggered only when meaningful events occur rather than being forced by a global clock. And this is why neuromorphic systems can achieve much better efficiency as compared to traditional clocked von Neumann computing. Before we get into the device level details of neuromorphic computing, let's take a quick historical perspective of this area. So of course, in the initial theoretical phase, there have been a lot of overlaps between AI and neuromorphic computing, and the theoretical foundations go back to as early as 1948, where Alan Turing wrote this seminal paper called Intelligent Machinery, which lays out the ideas that machines could finally mimic aspects of biological intelligence. In 1949, we saw two breakthroughs: the Macaulay-Pitts neuron model, which formalized the idea of artificial neurons, and also the big breakthrough of localized learning rules by Donald Hebb. And we will look at Hebbian learning in detail in our future classes. So what was very special is that Hebb made an empirical observation that the strength of connection between two neurons, which is guided by the synapse, increases if they are active at the same time. And this is popularly known by this adage, which is neurons that fire together, wire together. And this simple principle has become the foundation for all the modern ideas of neural plasticity and inspired many self-supervised learning algorithms in AI and neuromorphic computing. Next, we look at the big breakthrough that came in 80s with this revolutionary idea from Carver Mead, who was a VLSI pioneer at Caltech. So Mead's main contribution was that neurons and synapses could be directly implemented in silicon CMOS using these mesh-like VLSI circuits, as you can see over here. And this was called the silicon retina, an artificial retina chip that mimicked how biological eyes process visual information at the sensor level by converting light into spikes, just like the real retina. So these early prototypes showed that hardware inspired by biology could achieve remarkable efficiency. So Mead not only worked in neural learning ICs, but also coined this term that we use very popularly nowadays called neuromorphic computing. The next set of developments happened in early industrial efforts by Intel through their ETAN project and IBM through their ZISC processor. So ETAN, which stands for Electrically Trainable Analog Neural Network Processor, was the first designed on-chip learning and low-power analog processor. And you would be surprised to know what were the devices that were used in this feedback synapse array. They were nothing but charge trapping floating gate cells, which has now become the flash memory. Next, IBM in 93 came up with the ZISC processor, which is the zero instruction set computer chip, which is inspired by neural networks. And this implemented massive pattern matching without a conventional set of coding or conventional instruction set. And this was one of the early steps towards hardware AI accelerators. At the same time, neuroscience itself was advancing in the understanding of learning rules like spike time dependent plasticity, which later inspired neuromorphic circuits. We will look at detail in what is spike timing dependent plasticity. It is one of the most popularly used learning rules. And in present day, there is a lot of activity that is being pursued both in industry and at academia through chips like IBM's True North and Intel's Loihi, and in academia through the Spinnaker project in UK, the Synapse and Blue Brain project in US and Europe respectively. So a lot of public and industry funding is going into this very promising area for reasons that we have just described. But this is just one line of work where CMOS VLSI technology and conventional computing is used to create these event-driven neuromorphic chips. In parallel, there is a lot of effort in developing neuromorphic devices using emerging materials and eNVM technologies like RRAM PCM and MRAM also. And we have given some hints when we were studying these eNVMs in our previous modules. As we will see very soon, these devices are very promising because they can directly mimic the behavior of neurons and synapses, therefore potentially offering a pathway to denser and more energy efficient or scalable neuromorphic hardware. Another thing that I would like to specifically mention is the interdisciplinary nature of this area of neuromorphic computing, which honestly gets me very excited about this area. Unlike classical computer science or electrical engineering, which was the driving forces of traditional computing, There are a lot of ideas which are coming from neurobiology, chemistry, mathematical modeling, physics, material science, micro VLSI, computer science, which all go together in building these neuromorphic chips for next generation neuromorphic computing. Next, we will look at why is there this renewed interest in neuromorphic computing. Of course, the main reason that we have been harping about is regarding power consumption, but there are two other important aspects. But first, let's formally put down what makes these neuromorphic chips much more power efficient compared to normal von Neumann computing. So the first reason is the frequency and voltage of operation. As we have seen, the idea in modern day computing in CPUs and GPUs is to work at gigahertz of frequency at roughly 1 to 2 volts of voltage. This is very different from the regime where the brain is working. So the brain typically works only in tenths or at max 100 millivolts and works at very low frequency of roughly 10 hertz. And this very low frequency and low voltage is what makes the individual elements of brain inspired computing inherently much more energy efficient. The second reason that we have also discussed is the architecture. Since in neuromorphic architectures, memory and logic is co-located and there is a tight integration between neurons and synapses with local communication. The data shuttling is limited and there is massive parallelism which drives down the energy that is required to shuttle data back and forth. So we have been harping a lot about power efficiency as the primary driver for neuromorphic computing. But beyond this, there are two very important advantages that neuromorphic computing will have over traditional computing. The first, as I have shown, is the robustness to noise. Biological systems like the brain operate in really noisy environments with neurons which are misfiring, synapses which are unreliable, and even sometimes external sensory input and its encoding is not very perfect. Yet, the brain continues to function quite smoothly and reliably. And this is the promise even with neuromorphic systems, that it can tolerate noisy signals and device implementations which are not perfect. This robustness to noise, which is very different from traditional digital computing, which expects precision at each and every step. And this is what makes them naturally resilient and fault tolerant. In our own group, in our recently unpublished work, we have shown that artificial neural networks, which are made from more neuromorphic architectures like spiking neural networks or stochastic computing, really outperform when it comes to noise robustness traditional forms of implementing artificial neural networks. The second advantage is the ability to have unsupervised learning and adaptability. Unlike today's AI systems that require enormous labeled data sets and offline training, the brain learns on the fly. It adapts continuously to new situations through localized learning rules, as we just discussed. And the idea is that neuromorphic systems could inherit this property by intelligent design. They can learn and adapt from incoming data streams without requiring very energy expensive backpropagation retraining algorithms. And this has been successfully shown for small tasks and small networks, as we will discuss in future classes. So to finally conclude our discussion today, we contrasted the essential features between von Neumann computing and neuromorphic architectures, where we saw that neuromorphic architectures combine memory and computation in the form of spiking activity by doing parallel processing and communication which happens asynchronously. However, The big question still remains going forward. How do we implement such neuromorphic architectures in scalable hardware? While the brain uses neurons and synapses, your traditional von Neumann computing relies on transistors and memory elements. The exciting possibility is that we may not need to completely redesign the existing set of transistors and memory, and just by tweaking or re-engineering the existing computing and memory devices using the same fabrication process, they can be made to behave like neurons and synapses. If we can truly achieve this potential, it will open a pathway to large-scale neuromorphic systems which are built on the top of well-established semiconductor foundry processes. But in order to do that, we have to gain some understanding of how signal transmission happens in the biological brain through the interconnected web of neurons and synapses. And that is where we will begin our next class. Thank you very much for your attention. See you in the next class.